Okay, I think we'll get started with class. So first off, is there anyone out there who has questions on content, homework, final project? I know you're working on finding papers and working on finding project topics, and I've chatted with a couple of you by email, but I'd be happy to entertain any live questions here or talk about anything you want to talk about before we get started on slides. No takers? Okay, well, I'm available for office hours and questions anytime. So I want to make sure, especially that you're thinking about your final projects and doing something useful with the projects and learning something that you really want to learn, just like the papers. And so I'm happy to chat about that anytime, including how some of the polymer things that we're talking about in this class might relate to AM of other materials like metals or ceramics. I know some of you are not necessarily doing research on polymeric materials or AM of polymers. And so if you're really working on some other material set, or if you're only sort of polymer adjacent or polymer and composite curious and really want to learn about AM of something else, certainly we can customize the project and find some common ground in terms of things that matter for this class and how topics in this class might relate to other materials or other AM processes. So I'm happy to discuss, and basically the assignment for the final project is to just get started with a title, just get started with resources, make sure there's enough in the literature that you can make a good go at it. And so, of course, you're not locked in to the topic you choose, but the more work you do in advance, the easier it's going to be as we get towards the end of the semester and lots of things start piling up. So anyway, that's my advice on having a smooth final paper and presentation, and we can continue to chat about that. And I'll have a couple more check-in assignments to make sure we all stay on track. Okay, any questions? So we wound up on this slide last time, and we were a little hustled at the end of lecture. So I want to make sure to show you these two papers because I think they're really cool. So the first one at the bottom here is SLA that includes graphene. And so if you go to this link, like I did, find it right here, and you bring up this paper, the title of the paper is Graphene Reinforced Biodegradable Resins. That's interesting, but you know that graphene is black. And so one of the sort of pauses that you might make is saying, well, the graphene is going to absorb all the light. How do you SLA this material? But if you look through the figures, so they talk about making an SLA resin, how they formulate it, some printing characterization, which is cool, and we'll talk a little bit more about that. But they're producing structures. Let me first go to the pictures of the structures. They're producing SLA structures with this intricacy, and this is 0.5 weight percent graphene in an SLA resin compared to this type of structure that doesn't contain any graphene. And so usually when you see something black like this that's made from a commodity polymer, it likely is filled with carbon because carbon is a pretty inexpensive filler, and of course it makes things black. And so they're able to get enough graphene in here with enough fidelity of 3D printing that they can print some reasonable things. But by adding the particles or the graphene particles to the resin, you see the viscosity of the resin increase as you add 0.5 weight percent graphene. So they have their viscosity as a function of temperature curve for their standard SLA resin. And of course, you can look that up in this paper. And then when you just put a few particles in, 0.58% graphene, which isn't very much, you see the viscosity increase. So you do need to worry about the viscosity increase when you do composite SLA, but the payoff is pretty good in terms of mechanical properties. And so you see that the 3D printing resins have higher tensile strength, and they have reasonable flexural strength and flexural modulus. And so this is showing the advantage of adding any type of reinforcement. And if you look in the polymer composites literature, there's tons and tons and tons of papers on silica reinforced polymers, on graphene reinforced polymers, on carbon nanotube reinforced polymers. And so we would like to be able to take advantage of those composite effects in SLA resins. And of course, graphene is an easy and popular filler. And so people are starting to approach advanced SLA resins with these types of fillers. And so my message is not to avoid fillers just because they're black and you think they'll absorb all the light. You just need to tune your printing parameters, and we'll talk about tuning printing parameters in a second. But I wanted to highlight this paper because it was interesting. The other paper that we talked about was this silver nanoparticle paper. And we touched on this briefly last time, but I think it's worth looking at the paper itself. So if you go to this link right here, this is the paper. And so this is the diagram that we looked at before, showing that you can now grow particles inside of an SLA resin. So in this case, without the silver salt, this is just a standard SLA resin. And so you get something that looks like a standard SLA material in the A sample there. And so that's just business as usual. But as you put in this silver salt that reduces to silver nanoparticles in situ, you get samples B through E with various levels of silver salt in them. And now this is how you might do secondary reactions, or how you might get very uniform metal loading in an SLA resin rather than mixing in silver nanoparticles in the first place. Because if you put in nanoparticles, again, they absorb the light, they make the resin more viscous. Mixing in silver salts will make the resins a little bit more viscous, but the salt won't absorb light until it starts to turn into silver nanoparticles based on the top pathway right here, the reduction pathway. So when we looked at the patents and they talked about having a plurality of particles in the resin that do a secondary reaction, this is one of the ways that they do it, is to add something that can be reduced by radicals and you get secondary growth of particles. And we'll look at a couple more strategies today on this. So I just wanted to make sure to look at those papers and wanted to make sure to reiterate that these links on the bottom of the slides contain a lot more information if you want to take a deeper dive into what exactly were the recipes, what exactly were the printing conditions, what printers did people use, all of those sorts of things. And so I just wanted to cover that in detail at the start of this lecture. Any questions on this stuff? Okay, so we will move on to lecture 8.7, which should be in the box. And it looks like my computer is really working well today, so that's great. There's just two more little things that I want to cover in SLA before we move on to other stuff. And again, if you're interested in specific topics, if you want to do 5 more lectures on SLA, give me a shout. Or if you want to go back and cover stuff in FDM, or if you have another interest, we're going to talk about applications. We're going to talk about economics a little bit. We're going to talk a little bit about thermal stresses because I had a question on that. But we're getting to the point in the semester where I want to make sure that we're covering things that are going to be useful for you all going forward. And we've covered a lot of the major printing technologies. I told you we weren't going to do a lot on sheet lamination, but other than that, I guess if you're interested in sheet lamination, we can continue to talk about it. But we're getting to the point in the semester where I want to make sure that we're hitting some highlights for things that you all are interested in. So don't be afraid to send me suggestions or requests, and I'll do my best to cover them as I weave them into the lectures here. Okay, so we have a few more things to talk about in terms of stereolithography or vat photopolymerization in general. And one of the things that we haven't talked a lot about is this thing called a working curve. So a working curve is a vocab word for stereolithography, and it basically gives us an idea as to how the resin is curing under different conditions. And there's lots of ways to do this working curve, and each printer that you buy from a manufacturer usually has a working curve program that you can use with different resins to define the parameters, or the parameters are built in to the machine and you just select what resin you have from that company. That way you don't have to take a working curve. But as you develop SLA resins, or as you develop printing technology, this is a key part for learning how a specific resin is working in a specific printer. And it just so happens that Instructables has a really nice working curve tutorial that we're going to go through. And this Instructable was made by folks from Autodesk that built their own printer called an Ember. So they're going to talk about this Ember, which is not readily available now, but certainly the Autodesk people know what they're doing. And so let's go to this link. I think I have it queued up, and we'll hear about how to take this working curve and how to really tune in your printer for a very specific resin and very specific resolution. And I should say that the person who wrote this, Brian Adzima, and he's got a funny Instructables name. But anyway, Brian got his PhD in polymer chemistry from Chris Maniszewski. And so Brian is a friend of mine who used to work in the Ember team in Autodesk. And so he's got some really good things to say. And if you look him up on LinkedIn, you can see what he's up to now. He's started his own 3D printing company in San Francisco. But anyway, let's hear about this working curve if this video works.
It is vital to determine the precise amount of light energy, or exposure, needed to cure a 3D printable resin. Why? Let's say we have a model with small positive features. These square posts range from 500 to 100 microns in width, and they're 4 millimeters tall. Now we print it on an Ember with the proper energy exposure. All of the features turned out except for the very smallest one, the 100 micron wide post. It started to print but collapsed because it was too thin. When we print this model with only two...
I just want to pipe in here that this video also gives you an idea of feature sizes, overhangs, unsupported type material that you can do with SLA, at least in the context of the Ember. So this starts to give you a physical picture of what some of the limits are for what you can build. So just pay attention to that.
Thirds of the energy, neither the 150 or 100 micron posts are formed. With half the light energy as the original print, only the 500 and 450 micron posts form, but they're thinner than they should be. For models with small negative features, too much light energy can be a problem. If we dial in the exposure, the 500 micron and larger gaps are clearly resolved. The 250 micron gaps are partially resolved, but the 125 micron features are completely filled in. If we add just 33% more light exposure, the 250 micron features are completely filled in, and we have effectively lowered our resolution. So how easy is it to find the correct exposure? These prints each take roughly 30 minutes to print at 25 micron layers. So if we vary the light energy by varying the exposure time, we might need to try about 10 different exposures before we can dial it in. And that's just for the 25 micron layers. What if we want to print at 10, 50, or 100 micron layers? So in total, it could take upwards of 20 hours worth of printing to find the right exposure times for our resin. But if we're clever, we can get the same information from a single print. We start with a diagnostic print file consisting of 32 slices. The slice images create a panel of 32 rectangles where each rectangle receives a distinct amount of light energy. The rectangle that is illuminated in every slice receives 32 times the energy as a rectangle that is only illuminated in the first slice. The pattern is randomized to minimize the effect of possible unequal illumination across the build area. Unlike a normal print, we don't fill up the tray with resin. Simply pipette a
Okay,
layer of
so
resin.
the Ember is a very small printer. So you can see the build tray right there is only 1.5 by 3 inches or something like that. So when we look at a picture like this is indicating that build tray. So in some printers, they're square, but this is basically everywhere where the vat is exposed to light. So when they're talking about unequal illumination, which we'll discuss in a couple slides, they're talking about as you move the laser around, the laser might not have the same intensity at all points on this window. And so this is basically when we're looking at pictures like this, it represents how the light is coming up through this gray area right here, which is the PDMS window. And of course, the light source in the Ember is coming from the bottom where that gray cylinder is, where the little screen readout is. So this is a bottom-up DLP illumination. So the Ember is not a raster scanner, it's a full DLP setup.
Simply pipette a layer of resin directly onto the PDMS window. Also, the tray does not rotate between layers, and we do not use a build head. Then we run the print file, which only takes a little over a minute. After the print is complete, we wash off the uncured resin and are left with a thin film with distinct panels. The darker panels received more light and are thicker, ones that received less light are thinner, and some panels never reached a threshold amount of energy and did not solidify at all. Next, we use a thickness gauge to carefully measure the thickness of each panel, then record the measurements onto a spreadsheet. The spreadsheet creates a plot of thickness versus light dosage. We use a logarithmic fit to extrapolate into the layer thicknesses we're interested in, namely 10 to 100 microns. Then we locate the layer thickness we want to print at and find the dosage required to cure. For the Ember printer, the irradiance is about 20 milliwatts per centimeter squared. This gives us an exposure time of 1.25 seconds. But we're not quite there yet. Ideally, a 3D printed layer would solidify all at once when exposed to light. However, in practice, it is more complicated. We wish the light intensity was perfectly uniform throughout the thickness of the layer. In reality, the light intensity drops off as we move up through the resin.
This is true for even thin layers. So even 100 micron layers, even 50 micron layers, because these resins absorb so strongly, there is a gradient in polymerization as you go from the window into the resin. Of course, if there's a dead zone, there's a gradient at the window side too, which is another thing that we've discussed. But even though this looks like a big gap here, these resins absorb very strongly. So within 100 microns, the light intensity is dropping off. So it's something to keep in mind.
So the layer begins to form where the light intensity is highest, at the surface of the window. And over time, it grows towards the previous layer. So the exposure time we calculated is only the minimum time it takes to cure a film. In practice, for the layer to fully adhere to the previous layer, the exposure time is usually between 20 and 40% more time than is specified on the graph. You can figure this out with a handful of test prints. Printing the panels, measuring their thickness, and calculating an exposure time takes about 30 minutes on Ember. This process works well for a wide range of 3D printable resins. Thanks for watching, and please subscribe if you'd like to learn more about research.
Okay, so that's all very interesting, and it gives you an idea of what's needed to develop high fidelity prints if you're having resolution issues, if you have a new resin and you don't know how to cure it. Of course, this relies on being able to change the printer settings, which if you walk up to a carbon printer with a certain carbon resin, the printer is already calibrated for that resin. And so you don't get to change exposure settings at all. But if you're interested in SLA research or materials research or printing research, this concept of a working curve and establishing the cure of your material in a specific printer is useful. So that's a concept that you should know about. any questions on that? Any comments on a working curve or getting resins to cure, or how you figure that out? Okay, the test structures that they showed were really interesting and were a mixture of different calibration structures. We won't talk too much about the mechanical design of calibration structures. There's overhang standard structures, there's pillar standard structures, there's all sorts of things. There's bridge standard structures. Those are some of the things that will be discussed in your design course or in your printer technology courses, but these calibration structures are available so you can really gauge how well the printer is working for whatever given material you're interested in. So it was mentioned that in the build platform, that's usually, in an Ember, it's only, say, uh, 1.5 inches by 3 inches or so, but we know that SLA platforms can be on the order of tens of inches in each dimension. Viper Pro is 2 feet by 3 feet or something like that. And the light intensity can vary across the build platform, either in a DLP setup or in a raster scanning setup. So for DLP illumination, or laser raster scanning, because the light has to travel a different length and the optics are slightly different, how the angle of incidence of the light hits the window, the intensity of the light can vary across the build platform. So if you go to this Instructable here, which is by the Ember Group or Brian Adzema again, this shows you statistically how to map out the light intensity and how to map that back onto the working curve. So they don't have a nice video for this one, so we won't watch this. But if you're interested in how to statistically correct for light intensity differences, this is a nice how-to in terms of getting good uniformity across the print bed. Because say you're printing a structure here, but you also want to print a structure over here and over here, these 3 different areas on the print bed, or these 3 different parts, if you're batching a number of parts together, might receive different illumination. And so that needs to be corrected for in the printing software or in the curing time. And so making sure that you're able to vary those conditions across the bed is important. And right now, people are working on printer control software for catching these differences and illuminating the bed differently at different times or at different times in the print. In a lot of instances, that's baked into proprietary build software. But those are some of the effects that advanced SLA software is trying to combat as the printing speed goes up, as the resolution requirements increase, and as SLA gets more sophisticated in terms of printing final parts with engineering properties rather than just printing prototypes as in the past. Any questions on those engineering things or on those illumination or working curve issues? All right. So there's just a couple of things I want to talk about in terms of photo initiators, additives, a couple last things that are in these resins that aren't necessarily obvious or that we haven't talked about in detail. And so all of these blue boxed figures are from this paper. Sorry, hold on, let me find the paper reference. No. Yeah, they're from this paper right here. So let me see if I can copy this thing and then paste it back up here so we don't get too lost. There we go. So that should upload to Box and the slides will update. But anyway, this is a really nice paper. It's more on the chemistry side of things, but of course, in developing these SLA resins, you really have to know just a little bit about the chemistry, or at least that Darocure 1173 is a photoinitiator with this chemical structure, and you can use this for radical photopolymerization of acrylates and methacrylates. So having some guides or having some knowledge about how to pair up photoinitiators and monomers is a good idea. And of course, if people want to dive into the polymer chemistry of it, we can chat about that more. But we'll just talk about the general themes and how to know what you're dealing with at what time. So these type 1 photoinitiators, Norrish was a person who came up with type 1 photoinitiators, basically work the same as benzoyl peroxide. So you send in a photon that's absorbed in this molecule right here. This star is an excited state. And the excited state fragments a molecule into 2 radicals that can then react with the monomer and then propagate, as we talked about for acrylates and methacrylates. So if there's a type 1 photocleavage, there's also, there's a number of type 1 radical photoinitiators. And so Darocure 1173 is this one right here that we saw in the previous slide. We've referred to Ergocure 184 and some other Ergocures. That's I-184. Here's Ergocure 651, and here's Ergocure 369. And so these are just different types of photoinitiators that you can buy from the Sigma Aldrich catalog or wherever you buy your photoinitiators. And so this gives you an idea that these are all radical photoinitiators. You can look up the absorbance spectrum for each photoinitiator. And so all you need is the UV-Vis absorbance spectrum for the molecule. And that will give you an idea of where you should illuminate these different photoinitiators to line up the light source, because you're usually using a laser light source, and so it'll be 1 wavelength. Or you have a broadband light source, so you need to figure out what the emission spectrum of your light source is to figure out how much light you have at different wavelengths. And you need to line that up with the right photoinitiator. But all of these are radical photoinitiators, and you know that these will be used with acrylates and methacrylates, some styrenes in general. And if you have type 1 photoinitiators, there's likely something called type 2 photoinitiators. And type 2 photoinitiators are really easy to remember because they take 2 molecules. So type 2 require 2 molecules. Just what this says from the paper right here. So you have a 2-component system where you have a light absorbing molecule or sensitizer. So this thing is sensitizer. It absorbs the light, and you know that H nu corresponds to a photon, and this is the excited state again. So you have the light absorbing molecule, and then this co-initiator, and this is an old school term, but they call that the synergist. in some very old photochemistry books, which is the co-initiator. When you have those two molecules together, you get a radical on each molecule. And so you still get two radicals based on this one photon, but you get it by different mechanisms. And so no longer are you fragmenting your sensitizer like you are in this reaction. So you start with one molecule in a type 1 Norrish photocleavage, and you get two radicals from that one molecule. And in type 2, you have two molecules and you get two radicals. And so that's sort of in the weeds chemistry details. But if you're looking at the list of 30 or 40 compounds that are in an SLA resin, you need to know which are which. Oh, I see a chat here. Hold on one sec. Let me read it. Is direct laser writing, does it fall within SLA or is it a separate technique? So I assume, Nathaniel, that you're talking about direct laser writing stereolithography, because direct laser writing lithography is not a three-dimensional technique. That's a nanofab technique where you're doing like laser writing of masks in a clean room or something like that. Or are you talking about stereolithography or lithography?
I believe the stereolithography, it's with reference to the new DWL 66 plus grayscale lithographer that the MSC is getting, I think currently.
Well, let's look at, go ahead and say the name, DWL.
Yes, sir, DWL 66 plus grayscale lithography. It was the assignment I was going to do my homework on, but I was unsure if that might fall into the category of SLA and I would want to find a different paper.
Well, so this machine, I'm almost sure if the nanofab is getting it, is a mask writing machine. So I don't know that this is, so this makes diffraction gratings, okay. Let me see what the fact sheet looks like. So this is exactly like a raster scanning. Well, it's both raster scanning with a 2D focus, so you can do different parts of the wafer. But because this is writing on a wafer, this is lithography, which is 2 dimensions, and the third dimension is very thin, versus stereolithography, which is 3 dimensions. So it's exactly the same type of process, but this doesn't build up 3-dimensional structures, except if you modify the intensity and you have differential etching. And so you can get these sort of slope structures, you can get intensity gradients that are transferred to a single layer, but this is not a vat type process. This is more in the realm of 2D or 2.5D. So things like you could compare this to just lithography. So UV lithography of Pentium chips or something like that. The closest nanofab instrument that they have to what we're talking about in stereolithography is something called the nanoscribe. So a nanoscribe is a brand name for a micro 3D stereolithography. So it's basically, it looks a lot like this, but it actually has 3-dimensional capability where you can build very small structures. And so this DWL instrument is not stereolithography, it's just lithography. And so that's 2D on a wafer versus a real 3-dimensional system where you have differential layers, because there's nothing in the DWL that can make the next layer, right? There's no stepping of the Z height in this instrument, this is only stepping around in 2 dimensions on a wafer. Whereas all the processes that we're talking about, you have steps in the Z height, which help you build up a 3-dimensional object rather than just a quasi 2-dimensional object on a wafer. Is that reasonable, Nathaniel?
Yes, very much. Thank you.
Yeah. So I think for your project, or for people who are interested in nanofabrication, something like the NanoScribe, I would encourage you to take a look at. The NanoScribe is really interesting because it uses 2 photon resins, and we'll talk about those if we have time. They're just a little bit different type of resin than we're talking about here, but it's actually a very similar process to what we're talking about. However, it's on the micro scale, and it's done through a microscope objective versus the sort of regular size objects that we've discussed before. So where were we? Yeah, so there's lots of variations on this. You saw what Nathaniel's interested in. There's a lot of variations of how you do this type of lithography, but this is called stereolithography because it's in 3 dimensions. Lithography is generally 2 dimensions. Okay, so that's type 1, type 2 radical photoinitiator. So again, this is, let me find my stencil here, or my pen. This is radical photoinitiation of acrylate and methacrylates. Great. And so you need to pair the machine light source with the, whoops, oh, that's not good. Absorbance spectrum of the photoinitiator. And so oftentimes the resists are named for the type of light or the type of exposure that they want. In stereolithography resins, it's not quite as straightforward, but oftentimes if you know the photoinitiator, whether it's a Darocure or an Ergocure, the light sources are tuned to activate these initiators, or these initiators were specifically made to pair with helium cadmium lasers or other light sources, YAG sources that are well known, or helium neon sources, etc. And so, or UVA, UVB based DLP if you have broadband UV illumination of your digital mirror device. And so there's a lot of rules of thumb out there depending on what printer you have, what photoinitiator you should use, or if you're designing a light source around a very specific composition, excuse me, you can figure out what light source you need for a given photoinitiator. But you need to pair these together so you get good initiation of your material and you get good curing. Because if you're trying to cure a resin with the wrong light source, it's not going to cure, because the wavelength of the light really determines your initiation. And without the generation of these radicals, nothing is going to happen in your resin. And so you want to make sure that you're using the right light with the right resin. Any questions on that? All right. So the one thing that we haven't talked a lot about, and that's in this same paper, so let me just copy that link and put it here so we don't forget. Oh, no, I don't want to cut it. Copy. Sorry about that. Just want to make sure my referencing is obvious here. There we go. Okay. We haven't discussed this idea of a photoacid generator and how they're used to initiate what's called cationic polymerization. So we've talked about radical polymerization, where you're using free radicals, and you've seen that over and over and over again. And most of the resins out there, especially the cheap ones that are easy to use, are acrylates and methacrylates. But a lot of the engineering resins, and sometimes it's hard to figure out if you have a cationic resin or a radical resin. You really need to dig into the MSDS or into the company's technical literature. Cationic polymerizations are used for epoxides or epoxies. Epoxide is this little functional group right there. So it's a 3-membered ring with an oxygen in it. So that's called an epoxide functional group. And epoxy is the material. And so just like your 2-part epoxy that you squeeze out of the dual syringe from the hardware store, it's the exact same chemistry. Usually they're amine cured epoxies, not this photoacid generator epoxy, but this is a standard polymer chemistry that's used in some of the engineering resins because you get very tough materials. And so because in a lot of radical polymerizations, acrylates and methacrylates, you get brittle materials. Epoxies are really used for tough, durable, strong materials. And you don't react epoxides through radical means. They must be polymerized, at least in photopolymerization, cationically. You can polymerize epoxides other ways, but we won't talk about that chemistry because we just want to cover things that are relevant to additive. So these photoacid generators, so these are cationic photoinitiators. And so when you shine light on these salts, so these are all salts because they have cation, or the anion and the cation. When you shine light on these things, they create an acidic environment that can then react with this epoxide. And so these they're called photoacid generators because they make an acidic proton based on shining light on them with a photon. And that's a completely different mechanism than making a radical when you shine light on a molecule. So we won't go into depth into the chemistry other than to say this is our now photoacid generator. This is our monomer or oligomer. And from a photoacid, you get a proton right here. And that proton is what causes this cationic ring opening polymerization. And that's what gives you your polymer. Either through chain growth with another epoxide monomer, or through chain transfer with this diol here. And that's in the weeds of the polymer chemistry. But what you should know is that, and it goes through it a little bit right here in terms of the strength of SLA resins and when different resins are used, whether you have a radical, acrylate, methacrylate, resin, versus a photoacid epoxide resin. And you might say, well, why don't we use epoxides all the time? Turns out they're more expensive. The resins are less stable. They're harder to deal with in some ways. And so we don't want to use photoacid epoxides for our SLA unless we absolutely need the properties, because acrylates and methacrylates are cheaper, they're easier to use, they're more stable, they're not as toxic. And so we need to be able, if we're interested in the resin chemistry, to dig deep enough to figure out what's in the resin for one versus the other, because it's not necessarily that 3D Systems is going to tell you, oh, this is a photoacid epoxide based resin, or this is an acrylate and methacrylate resin. The companies selling these resins don't always want to tell you exactly what's in there or what the mechanism is. They'll be like, just pick the right setting on the printer and here you go, because they want to keep some of their polymer chemistry under wraps. But with a little bit of knowledge here, we can start to discern exactly what's going on. Any questions on that? We're not going to go crazy here on polymer chemistry and mechanisms, but for people who are interested in digging into it in SLA resins, this gives you a place to start. And any questions? All right. There's a lot of other stuff that goes into SLA resins. There's dispersants, there's pigments. You know, you get if you need a blue SLA resin, you can buy one. And so there's a lot of other stuff in there. But one of the important things that acts on what we've just talked about are stabilizers and light absorbers. And so radical stabilizers or cationic stabilizers shown right here, basically these prevent resin from polymerizing in the bottle. Or they prevent the resin from polymerizing when you just take it out of the bottle and you expose it to light in the room. And so these are reactive molecules. And so the epoxides and the acrylates and methacrylates are ready to react. They'll react under thermal conditions. So if you ship your resin to Phoenix, Arizona in the summertime and it sits on your porch for a day and it's 120 degrees Fahrenheit outside, that could certainly have an adverse effect on your resin. But time will also do the same thing, or stray light will also do the same thing. And so lots of times there will be radical stabilizers or cationic stabilizers added to the resin to stop unwanted polymerization. Now, this, if you add too much of this stuff, of course, it will stop the photopolymerization as well, which is not good. But these act like a preservative. So BHT is used as a preservative in lots of different areas. But these basically act as preservatives to enhance the shelf life of the resins so they don't polymerize prematurely. And so even though this might impact the photopolymerization a little bit, it really helps with shelf stability of the resins. Light absorbers, on the other hand, basically compete with the photoinitiators for absorbance of the photon. And so remember, these absorb H nu and they inhibit activation of photoinitiator. So that sounds counterintuitive, right? I'm trying to do a photopolymerization. So when I send in light, I really want light to cause this reaction. But I'm going to add some inhibitor in order to prevent too much light from being absorbed in any one area or in any one photopolymerization event. So we use radical inhibitors to prevent premature gelation, but we often use these light absorbers to reduce the depth of penetration to get higher resolution. So even though this is very counterintuitive that we're going to add light absorbers to reduce depth of penetration, this allows us to increase resolution. We saw on the previous video that there's a gradient in absorbance. So let me see if I can quickly just go back to that. I didn't close the tab. So remember, we saw this gradient in the illumination, even for very thin layers. And so absorbers are basically going to suck up the light that is starting to fade off and make this cutoff much sharper. And so you won't get any sort of photons that are just causing a little bit of polymerization. Basically, the absorbers shut off the lowest parts of the gradient, or the least intense parts of the gradients. Or if you have a scratch in your window and say you have a weird reflection or something, so you have some weak light leaking out from your build path or something like that, the absorbers tend to compete for those photons, so they won't allow radical polymerization if you just have a little bit of light around. And so the upshot of this is that they increase the optical density of the resin, and so they allow the photoacid generator or the radical photoinitiator to work a lot better, and you don't have to deal with this stray light issue. So that's interesting, and that's counterintuitive unless you really study a lot about how to increase the resolution of these resins. The same sorts of tricks, so the same concepts are used in lithography resins for nanofabrication. And that's where a lot of this technology comes from. So photoacid generators were invented to really do lithography of Pentium chips and other memory chips on wafers. But a lot of that has been co-opted to increase the resolution of these stereolithography, or these 3D stereolithography resins, or these 3D techniques. So if you're interested in going way in and looking at all the different light absorbers, looking at quantitative relationships between how much absorber and the resolution that you can get, this gives you some guidelines in terms of, okay, these are only added in very low quantities, 50 to 200 ppm, but these are really important components of the overall resin. So if you want to dive into the composition of commercial resins more and more, now you're aware of some of the other components rather than the monomers and oligomers that give you the ultimate material properties. And this is why a lot of these stereolithography resins are treated as hazardous or reactive chemicals, because all this stuff is still in the resin after you make the part. And so if you FDM a part out of PLA, you know, PLA is a pretty benign plastic. It's not a big deal. It smells a little bit when it's heated up because of the additives that they put in PLA when you do material extrusion AM. But in general, thermoplastics are not too hazardous. These liquid resins are much more hazardous because they're reactive chemicals, and everything is stuck in there after you make the part. Even when you wash it, you're just washing off a lot of the surface layers. You're not really getting in there and extracting all of these different reactive species from your SLA part. And so this is why SLA resins have to be handled with more care, and it's less common to be using these outside of a controlled environment. And so that's something to remember when you encounter stereolithography resins. It's just not the same as reels of PLA or ABS. Any questions on this? Any questions on additives, stabilizers, light absorbers, things like that? Okay, well, I just highlighted one paper again that's shown right here, but there's lots and lots of papers on this from the photochemistry literature. So depending on what your expertise is, there's lots to do here if you're interested in learning more about these things. All right, we have one more thing I want to talk about in SLA. And so I think that should be an 8.8, which is right here. So if you look in the box, this lecture 8.8 should be in there. And this is a really interesting topic, and we're just going to talk about a couple papers. But, you know, this class is about polymers and composites. But in these couple of papers that we're going to talk about, they basically use polymer precursors and then do what's called pyrolysis, or they heat up polymers and then they obtain a ceramic. And these are called polymer derived ceramics, or PDCs. And you'll see some of the chemistry here in a second. But this is really cool because now you can do stereolithography and get high resolution structures and turn those into ceramics just through this pyrolysis step. So this is a nice paper right here. I suggest you check this out because it's just really cool. So they're doing SLA, or they're doing the DLP variant of SLA. And this is a polymer fresh out of the SLA machine. And then pyrolysis at 1000 C in inert gas like argon or something like that. Of course, if you just heat up a polymer to 1000 C with a lot of oxygen around, you turn that polymer into CO2 and a little bit of ash and water. But if you prevent the complete oxidation of the polymer and you just do pyrolysis, you get this thing, which is a ceramic that's smaller. So you have shrinkage, because at 1000 C, you're going to lose some mass. But you have this ceramic that basically has the same shape, it's just smaller. And so this is called a polymer derived ceramic because you start with the polymer, you pyrolyze it, and you get a ceramic material. And so this is one of the ways that people are doing very intricate ceramics using stereolithography without having to process a ceramic slurry. So if you've taken Professor Messing's ceramic processing course, or if you've ever made a ceramic in the lab before, usually you start with the powder and you mix that powder with the binder, and then you shape it, you dry it, and then you kiln it. It's just like making a pot. That's how, in art class, that's how a lot of ceramics are still made. This process doesn't use a powder at all. It uses a polymer, it uses a flexible polymer in this pyrolysis process. So this is a more expensive way to make ceramics, but this is one method for making some high performance, intricately shaped materials that you just couldn't make another way. So these are some figures. Of course, this is the polymer. This is a ceramic. We'll talk about chemistry in a second. But what's cool, they show the intricate shapes that you can get, and you can see the DLP pixels in the shape. And we saw this on the hearing aid video. You could actually see the pixelation of the light source in the shape of the material. And some people actually use that to identify the manufacturing method that was used to make these different things, but that's in the realm of reverse engineering or material forensics. But that's just a really interesting facet of what's possible. And you can imagine that this type of ceramic can't be made by any other means. And so in general, we're going to go from something like a silicone or a PDMS or a siloxane And siloxanes have the general polymer formula SiO is a repeat unit. And of course, you have different functional groups on the silicon, but this SiO is not that far away from SiO2 or silicon oxycarbide. So SiO2, of course, is quartz or silica. It's hard to get to that, but this silicon oxycarbide is a ceramic. And of course, you could think about silicon carbide, which is really hard to get to if you get rid of the oxygen. But these are all variations of polymer-derived ceramics that you can get by printing silicones. And we've already talked about elastomers and other things like that. And so this is one of the routes that people have worked out in polymer-derived ceramics that's common. Oh, I see a question here, 1 second. Can pyrolysis be performed on both thermosets and thermoplastics? The answer is yes. And so the question is, what polymers are useful for pyrolysis? Because if you take a polyester and try and pyrolyze it, there's too much oxygen in a lot of those polyesters. And so you need elements like silicon, like nitrogen, and you can't have too much oxygen and carbon in your polymer. Otherwise, it will just burn, because in order to get a combustion reaction, of course, you need carbon and you need oxygen. So you need polymers with silicon, nitrogen, phosphorus, and not a lot of carbon and oxygen. And so it turns out that ceramists have been working on polymer-derived ceramics for a long time. And so there's a list of polymers that works in pyrolysis. There's a list of pyrolysis conditions and how to go from something that looks like a polymer powder. So these are all siloxanes of various sorts. And you do hydrolysis and condensation, and then finally you get some sort of polymer network, and then you pyrolyze to get PDC. And one of the ways that you can tell if you have a reasonable polymer-derived ceramic or not is that you get this. This is not a great x-axis, but this is percent weight loss. And so at high temperatures, up to 1,000 degrees Celsius, these two materials only lose 50% of their weight. And that's why you get the shrinkage. So ceramics are more dense, they're heavier. And so as you lose mass, of course, you get this shrinkage in physical dimension. So that's seen here, and you can also measure the shrinkage. But these polymers will be completely combusted. So those aren't good candidates at all for pyrolysis or polymer-derived ceramics because they're gone. They experience 100% weight loss at low temperature. They're completely dead. But these polymers have high ceramic yield, where the polymer has pretty good conversion to the ceramic of interest. And those are the types of polymers that start to work. So whether this is a thermoset or a thermoplastic, you can actually have PDMS or silicones that are both. You can work out this pyrolysis for these polymer-derived ceramics. And so we've done polymer-derived ceramics both with direct ink writing and with stereolithography. And this is a growing and interesting field for SLA of intricate ceramic structures that you couldn't hope to get otherwise. Any questions on this so far? Okay. There's another really nice paper, and they take advantage of what's called elastomer-derived ceramics. So that's another name for polymer-derived ceramics that are flexible polymers like silicone. And so you take your 3D printed elastomer in step A here. And so this is direct ink writing. And we know that direct ink writing is a subclass of material extrusion, AM. And so you 3D print your elastomer. And then what's interesting is that they put in a metal wire, or they strain this in order to get a deformed elastomer. So they have a pre-strained precursor. This is just a flexible thing. That's fine. And then they heat in argon or under vacuum. So this is called pyrolysis. Or sometimes it's pre-pyrolysis. And they call this ceramic origami. They etch it to get rid of the wire. And then they heat this thing in air. And it's white because air plus high temperature gives SiO2. So if you have a lot of silica in there, silica nanoparticles, of course, are white. Silicon oxycarbide is black. And so as you look at the different diagrams here, and this is very complicated because they're doing a couple different things, you can get either silica majority composites, ceramics, or silicon oxycarbide phases. And now you can get curved silicon oxycarbide, which is just really hard to do otherwise. So it's really easy to make curved polymers. Of course, if you have an elastomer, you just bend it the way you want, and then you do the pyrolysis under strain, and you can get these curve shapes, which is just really interesting. And they've taken it further, so they examine all the different phases that are formed. So if you're interested in polymer composition, you can check out this figure. But they've done all sorts of stuff. So they've done these different peak and valley type structures. They've evaluated the stress strain curves of these things. They've made these curved ceramics. They've also demonstrated some really intricate structures. So, you know, in SLA, printing something like this is totally possible in polymer, but now you can translate that. So once you have your 3D printed elastomer, you can translate that to a polymer derived ceramic, or as they call it, an EDC in this paper, elastomer derived ceramic, but it's basically the same thing. And then first and second is just whether it's been pyrolyzed in inert environment to get silicon oxycarbide, or then you treat it in air at high temperature and you get back to a silica phase. So this is cool because now, rather than worrying about polymer lattice structures, you can take those polymer lattice structures and you can translate them into ceramic lattice structures. And these types of ceramics, as I said before, are just really hard to make by any traditional ceramic processing method. Any questions on that? And of course, you can use these ceramics as investment casting molds or as other things. Of course, ceramics are useful for lots of things, including structural materials. And so you can imagine the flexibility this gives you in terms of ceramic material design. And of course, a lot of engineering materials are evaluated on this Ashby type plot where you're looking at some sort of mechanical property versus some sort of density. Or in this case, they're looking at compression strength. There's specific compression strength. So specific properties are per gram versus the dimension of the structures. And so they show that silicon oxycarbide lattices, and here they are right here in terms of the strength versus the density. These have really outstanding properties that are, you know, just as good as some of the other well-developed engineering materials out there in terms of lattices, in terms of honeycombs, in terms of other types of ceramic structures. So this approach of using SLA either as a template, so we won't talk much about template synthesis, but you could imagine making a cavity and using that in molding, as we talked about before, or taking that polymer template and transforming it through pyrolysis in this case into a ceramic is a really interesting way. And this is how new ceramics are coming online. This is how you translate some of the things that ceramists have known for a long time and how to get new structures that might do something useful. So any questions on this? Okay, so that is all we have to talk about for stereolithography. So if I'm missing something, someone wants to cover something specific, just let me know and I can work that into future lectures. On Thursday, I have an all-day conference, and so we'll have an evening lecture on Thursday. I'll send out a Canvas notice on that, but we won't have lecture at the regular time on Thursday because I'll be in a different conference, but we'll have lecture likely at 5 or 5:30. So I'll send out an announcement on that. And of course, it'll go on YouTube. I know that there are evening conflicts for lab work and other classes. And so I apologize for moving the synchronous class, but you'll have the online resources. And we'll start a new topic on Thursday. I think we're going to do a little bit about thermal stresses because I was asked a question about that. And then we'll move on to other things. So any final questions or comments before we end today? All right, well, don't forget your homework. Don't forget thinking about your end of semester project. And I will see you on Zoom a little bit later on Thursday, and you'll see an announcement about that. Thank you very much.
Thank you.
Thanks.
Thank you.